Hi, this is Mrs. Jackson. This is section 2 of chapter 4 in Precalc CP, and this section is all about the standard form versus the general form equations of circles. We're going to be going back and forth. We're going to take the standard form and convert it into the general form, and we're going to take the general form and convert it back into the standard form. So in the last section, we looked at what the standard form of a circle equation looks like. And for one that is centered at h comma k, that equation is x minus h squared plus y minus k squared equals r squared. And the center of that circle is hk. And where we're really focused in this section is the general form. And the general form looks like this. It's got a, like capital A for a coefficient, ax squared plus by squared plus cx plus dy plus e, which is a constant, equal to 0. This would be what we would call the general form. So where does the general form come from? We'll take a look at an example, and all it is if we actually took the square of this first binomial and took the square of the second binomial and just kind of combined like terms. So recall, if we square a binomial, I'll just write it out horizontally. X minus 3 squared is x minus 3 times x minus 3. Likewise, we're going to square this binomial. And recall that when you square a binomial, maybe I'll just show everything. Everything's got to distribute, and consequently, squaring a binomial results in a trinomial. So you square the first term, you get x squared. Square the second term, you're going to get that 9. But you also have 2 of these negative 3x's. So you'll end up with a trinomial. Y squared, then you'll have your 16, and you'll have 2 4y's, if you will, so that will double it, and you'll get 8y. And so the pattern here you can see is, you square the first term, square the second term, and then you're going to have double the product of the 2 terms because you'll end up having the 2 negative 3x's. And so we end up having some constants here that we can combine. And so we just kind of rearrange the furniture. I have x squared plus y squared minus 6x plus 8y. And then we have 25 on the side equal to 81. And we'll just move the 81 over. And so you could subtract the 25, move it to the right, or subtract the 81 and move that to the left. That's what I usually do. And what do we get here? Negative 56 equal to 0 on one side. And that's it. That is the general form of this equation. One more example here. We'll do this one a little bit faster. So you square that first term, x squared, square the second term, which is 49 fourths, and you end up with twice the product of these terms. So 7 halves plus 7 halves is 14 halves, or this would just turn into 7x. And likewise, y squared minus 6y plus 9 equals 10. And then we have our constants that we can combine. Just kind of rearrange the furniture here. X squared plus y squared plus 7x minus 6y. We've got 49 fourths. If I subtract this 10, I'm going to have a negative 1 here. And I'll just combine those like terms. So I've got 49 fourths minus 4 fourths is 45 fourths equals 0. And that's it. So going from the standard form to the general form is pretty simple to do. Going in the reverse direction is a little bit more work, and the way we're going to approach that is using a technique called completing the square. Most people learn completing the square when doing quadratics. So you can use that technique to solve a quadratic equation that's not factorable. And it's also the technique that's used to actually derive the quadratic formula. So the object of completing the square is to create an algebraic expression that is a perfect square. That's the whole point. And so what is a perfect square? Well, a perfect square numerically would be like 25 or 49, 81, etc. But algebraic expressions can also be perfect squares. And here I've got 3 binomials here being squared. Let's just do this real quick so that we could see the pattern. We've got x squared minus 6x plus 9. We've got y squared minus 1/2 y minus another 1/2 y is going to be negative 1y. And then negative 1/2 times negative 1/2 is positive 1/4. And x squared 5/4 x plus another 5/4 x is 10/4 x. And 5/4 squared is 25/16. So I did these 3 examples out so that you can see the pattern. We are going to want to create perfect squares where ones do not exist. So I want to see this pure constant here in the trinomial, and how does it relate to, let me change color. How does that constant relate to this number here? So this is a negative 1 and this is 10/4. How do they relate? In every single case, when we create that perfect square, that third term, that constant, is exactly half the middle term squared, or the square of the middle term. So, for example, half of negative 6 is negative 3. That's what goes in here in the parentheses. So half of negative 6 is negative 3. Negative 3 squared is 9. Half of negative 1 is negative 1/2. That's what's going to go in the parentheses. And negative 1/2 squared is positive 1/4. Half of 10/4 would be 10/8, if you will, or 5/4. And 5/4 squared then gives you that constant, 25/16. So that's the pattern, and we're going to be using that pattern over and over to create perfect squares. Okay, so let's take a look at the first example. So we're just building a little skill for right now, and then we're going to apply this to circle equations. So we've got x squared minus 5x plus. How do we make this into a perfect square? So we've got something here we want to add to make this a perfect square, and whatever it is going to equal the square of a binomial. So half of negative 5 is negative 5/2, so that's what goes in here. Negative 5/2 squared is going to give you the positive 25/4. And by the way, it's probably worth saying, this is always going to be an add. This C here is always going to be positive, because if we square a negative, you're going to end up positive, okay? All right, so next one, what are we going to add here? Half of 1 is a half. And 1/2 squared is 1/4. Last example here. It looks complicated, but it's really not. All right, what are we going to add here? So half of negative square root of 3 is negative square root of 3/2. And negative square root of 3 over 2 squared, or negative 3 over, negative square root of 3/2 times negative square root of 3/2 is going to give you a positive 3/4. So this is the pattern we're going to be using, and you can see in every case here we have equivalency. So this perfect square here, this trinomial, is a perfect square, and it's written as its square here in the parentheses. Okay, so how does that relate to the general form of a circle equation? So here we could see we have the general form. Okay, we've got everything multiplied out, and we can't see from this general form what the center of the circle is. We can't see what the radius is. So we need to go take that back into the standard form. And the first thing we're going to do is rearrange the furniture a little bit. I'm going to move over outside the box here because it gets a little bit large. So I've got x squared, and I'm going to move its x term next to it, negative 10x, and then I'm going to make a perfect square out of this. And then I have my y squared plus 4y, and I'm going to make it into a perfect square. And then I have 10 over here. Actually, I don't have 10. I have negative 19. Let me erase that. So if I subtract this 29, get it over with its like terms, I have negative 19. And I'm going to leave a little placeholder here as well, and you'll see why in a moment. So we're going to start to look at making the perfect square. So we have negative 10. So I have x minus 5. Half of negative 10 is negative 5. And when I square that negative 5, I have 25. And then I have half of 4 is 2. And when I square that 2, I end up with 4. So I'm adding, if I look here as a balanced scale, right over this equal sign, I'm adding 29 units to the left. I can't randomly add anything to one side of an equation and still maintain balance or equality. So if I add that 29 on the left side of this equation, I have to add that 29 to the right side of the equation. And so I'm going to put everything together now. I've got x minus 5 squared plus y plus 2 squared, and that's going to equal 10. And now I'm right back here in my standard form. So with that, I can now read the center and I can read the radius. So the center of this is, let's see, we have minus 5, so the center is positive 5. And we're at positive 2, so that's a negative 2. And remember, this 10 is not the radius. That's r squared. So our radius is going to be the square root of 10. Okay, let's try one more problem here. I'll zoom in. All right, we've got x squared plus 8x. Leave a placeholder to fit in your perfect square. We've got y squared minus 2y. Leave your placeholder. And I'm going to subtract the 17 from both sides. So over here, I end up with 1. And then I'm going to leave a placeholder. All right. So I'm going to turn that into a perfect square. I have x plus 4. Half of 8 is 4. And when I square that 4, I'm going to have to put 16 in here. Then I have half of negative 2 is negative 1. Square a negative 1 and you end up with 1. So I'm adding 17 on the left, so I'm going to have to add 17 on the right. Pull it all together. I've got x plus 4 squared plus y minus 1 squared equals 18. And we can read our center right off the equation now that we're in standard form. So our center is negative 4, positive 1, and r squared equals 18. So our radius is the square root of 18, and that can be written as 3 square roots of 2. All right, in this video, we looked at how to convert between standard and general forms of circle equations. Hope this helps.